motor theory. The learning objective for this section is to understand the fundamental concepts of both induction and synchronous motors to provide a good foundation for motor protection. Topics covered include principles of magnetism, principles of electromagnetism, the basic construction of AC motors, the operation of a permanent magnet synchronous AC motor, the operation of an induction motor, the operation of synchronous machines. In order to properly protect a three-phase AC motor, we should start with the fundamentals, a review of AC motor theory and motor thermal modeling. The best place to get started is with a review of some basic principles of magnetism and electromagnetism, which will form the foundation for a clear understanding of AC motor operation. Magnets have two poles. One is called the north, while the other is called the south pole. In this picture, we can see dotted lines that run from one pole to the other. These lines represent the magnet's force called magnetic lines of flux. These lines of flux are closed loops that by convention run from the North Pole to the South Pole, returning to the North Pole through the magnet. When the unlike poles of two magnets are brought together, their lines of flux combine and tend to pull or attract the two magnets together. We can conclude that unlike magnetic poles attract one another. Conversely, when the poles of the same polarity are brought together, the lines of flux produce a force that tends to repel the magnets apart. We can then say that like magnetic poles repulse one another. This attraction and repulsion plays an important role in the operation of an electric motor. When magnetic lines of flux cut through a conductor, a voltage and hence a current is induced in the conductor. The magnitude of the induced voltage and current is proportional to the speed at which the conductor is cut by the magnetic field and strength of the field. When current passes through a conductor, a magnetic field is induced around the conductor. The strength of the magnetic field will increase and decrease with an increase or decrease in current flow. There are several other ways of increasing the magnetic field strength with a given current. The first way is to wind the conductor into a coil. The lines of flux due to current flow will combine to produce a larger and stronger magnetic field. The more turns, the stronger the resulting field. To increase the strength of the magnetic field even further, the coil is formed around an iron core, as shown. Magnetic lines of flux can pass more easily through iron than air, and as a result, for a given current, the number of lines of flux produced by the current flowing through the iron core coil will be much more than that produced by the air core coil. Until now, we have been using direct current to study the properties of our electromagnet. If we connect our electromagnet to a suitable source of alternating current, we will see that the polarity of the electromagnet will change at the frequency of the applied current, and the absolute maximum and minimum field strength will coincide with the peak and zero current of the applied excitation voltage as illustrated. If a second electromagnet is brought into close proximity of our AC excited electromagnet, the cyclic expansion and contraction of the magnetic field of the excited electromagnet will in effect be continuously cutting the conductor windings of the second electromagnet, which will induce a voltage and hence current in the non-excited coil. This induced current will create a secondary magnetic field as illustrated. Let's take a look at the construction of an AC motor to better understand how it works. The two major parts of an AC motor are the stator windings and the rotor. The function of the stator is to create a rotating electromagnetic field when alternating current is applied to its windings. To see how this is accomplished, let's take a closer look at the stator's construction. The stator of an AC motor consists of a hollow cylinder with electromagnets forming the walls of the cylinder. These electromagnets remain stationary. The rotating field that they form when current is applied is referred to as the stator field. An illustration of how 6 electromagnets are wired and oriented to create the stator of a two-pole AC motor is shown in this wiring diagram. We can see that 2 electromagnets have been wired in series for each of the 3 phases. This is called a two-pole motor, because there are two electromagnets which contribute two electromagnetic poles per phase to the stator field. The electromagnets are positioned such that the resulting fields are 120 electrical degrees apart. The electromagnets in each phase of this two-pole motor are wired such that when current flows through one pole, or electromagnet, it flows in the opposite direction through the second electromagnet, or pole. For each phase, the resulting magnetic fields, and hence poles, facing the center of the motor are reversed as illustrated. We have labeled the electromagnets or poles in each phase as shown. To understand how the rotating magnetic field is formed, we will create a convention. When an alternating sinusoidal current is applied to any of the three phases of the motor's stator, if the current is positive, that is, the current is above the x-axis, the A1, B1, or C1 electromagnets will be said to have been connected and oriented such that the north pole is located on the electromagnet's pole facing the center of the motor, while the A2, B2, and C2 will have the opposite, or south pole, facing the center of the motor. It is easier to visualize the resultant magnetic field if times are chosen when no current is flowing in one phase. This occurs every 60 degrees. Let's choose a start time when there is no current in phase A. At this time, phase B has current flow in the negative direction, and phase C has current flow in the positive direction. According to our convention, C1 and B2 are north poles, while C2 and B1 are south poles. The magnetic line of flux will leave at the north pole of C1 and enter at the nearest south pole B1. Magnetic lines of flux will also leave B2 and enter the nearest south pole at C2. The resultant vector shown is the vector sum of the magnetic fields formed between the C and B poles. If we repeat this evaluation 60 degrees later, phase C will have zero current flow. Phase B has current flow in the negative direction, and phase A has current flow in the positive direction. With reference to our convention, A1 and B2 will be north poles, while A2 and B1 will be south poles. The magnetic lines of flux will leave at the north pole of A1 and enter the nearest south pole at B1, and magnetic lines of flux will also leave B2 and enter the nearest south pole at A2. The resultant vector sum of the magnetic fields is shown here. If we compare the angular displacement of the field, we can see that it has rotated 60 degrees. If this evaluation is repeated every 60 degrees for the rest of phase A's cycle, we will see that the resultant stator field goes through one complete revolution, or 360 degrees. With a frequency of 60 Hz, this means in 1 second the field will go through 60 complete rotations, and in 1 minute 3,600 rotations. The speed of the rotating magnetic field is referred to as the synchronous speed. The synchronous speed can be calculated by the formula synchronous speed equals 120 times the applied frequency divided by the number of poles. If we apply this equation to a 4-pole motor, the synchronous speed is 1800 RPM. Now let's take a look at the operation of a permanent magnet synchronous AC motor. First, we will mount a bar magnet in the center of the stator such that it can rotate freely about its own axis as shown. Then we will apply the three-phase power to the stator and note that the stator's rotating magnetic field will form. Opposite poles of the bar magnet and stator field will attract each other, resulting in the production of torque, which will cause the bar magnet to rotate about its axis at the same speed as the stator field. Permanent magnet synchronous AC motors tend to be very small, from fractional horsepower to less than 20 horsepower. They tend to be long and have a small diameter, resulting in a very low moment of inertia, making them ideal for high-speed positioning applications such as motion controllers. Another type of AC motor is called an induction motor. The rotor of an induction motor consists of a stack of steel laminations with evenly spaced conductor bars around the circumference. This is called a squirrel cage rotor design because the rotor bars and end rings look like the exercise wheel commonly found in the cage of pet mice. Once again, when power is applied to the stator, current flows through the windings and causes the expanding and contracting rotating stator field. This field cuts through the rotor bars, inducing a voltage, and hence a current in the rotor bars. The magnitude of the induced voltage, E, and hence rotor field strength, is determined by the equation E equals K phi N, where N is the relative speed that the stator field is cutting the rotor bars, phi is the flux density, and K is the motor constant. The rotating magnetic field formed by the stator causes the amplitude and polarity of the fields induced in the rotor bars to constantly change. This diagram aids in the understanding of how the attraction of unlike rotor and stator poles and the repulsion of like poles of the rotor and stator generates a torque on the rotor bars, causing the rotor to accelerate towards the speed of the stator's rotating field. If the rotor were able to match speed with the rotating stator field, the lines of flux in the stator wouldn't cut through the rotor bars, hence there would be no induced rotor voltage, therefore no secondary rotor field to interact with the stator field to produce torque. It is because of this that the rotor will accelerate towards the stator field speed, but will not quite match speed. The difference in speed is called slip. The difference between the rotor and field speed is sufficient to generate enough torque to overcome the connected load and losses. Slip is defined as the difference in speed between the rotor and the stator's rotating magnetic field and is expressed as a percentage of stator speed. Slip is load dependent. For example, if there is an increase in load, the rotor will slow down relative to the stator's rotating field, and as a result, the lines of flux in the stator's magnetic field will cut the rotor bars at a faster relative speed, inducing a larger voltage in the rotor bars, which in turn induces a larger circulating rotor current. This larger rotor current produces a stronger rotor field, which interacts with the stator field to produce a stronger torque to overcome the increase in load. If the load were to decrease, the rotor will speed up relative to the stator's rotating field, and as a result, the lines of flux in the stator's magnetic field will cut the rotor bars at a slower relative speed, inducing a smaller voltage in the rotor bars, which in turn induces a lower rotor current. This lower rotor current produces a smaller and weaker rotor field, which interacts with the stator field to produce a lower torque to overcome the decrease in load. Larger motors tend to be synchronous machines. The rotor of the synchronous motor is constructed similar to that of the squirrel cage rotor. In addition to rotor bars, coil windings are added. These coil windings are connected to an external DC power source through a slip ring and brush assembly. During a start, AC is applied to the stator, and the motor accelerates as an induction motor would. Once it reaches maximum speed, DC is applied to the rotor coils. This produces a strong, constant magnetic field in the rotor. This field locks in step with the rotating stator field. There is no difference in speed between the rotor and the stator's rotating field. Motor thermal modeling. The primary motor protective element within a motor protective relay is the thermal overload element, and within GE Multilin relays, this is accomplished through motor thermal modeling. The thermal model uses motor parameters supplied by the manufacturer in addition to real-time data such as motor current as inputs to a thermal modeling algorithm. The algorithm then calculates whether the motor is or is not in danger of being overheated. To provide a good foundation for thermal modeling, we will first start with a review of the following: common motor terms, motor thermal limits curves, the procedure for correct protection current transformer selection. We will then proceed with an explanation of motor thermal modeling and the contribution of each of the 5 key elements that comprise the motor thermal model. One of the most common motor terms is motor efficiency. Motor efficiency is an indication of how much of the electrical energy supplied to the motor is converted into output shaft mechanical energy and is expressed as a percentage. The rest of the energy is lost primarily in the form of heat, which can be damaging to the motor's insulation. There are 5 categories of motor losses. Core losses. Core losses are comprised of 2 components: the energy required to magnetize the core and eddy current losses in the stator core. Stator losses. Stator losses due to the I²R heating of the stator due to current flow in the stator windings. Rotor losses. Rotor losses due to the I²R heating of rotor bars as induced current flows. Friction and windage losses. Friction and windage losses due to bearing and air friction. Stray load losses. Stray load losses due primarily to leakage reactance fluxes induced by the load current. Core, stator, and rotor losses typically make up greater than 80% of the total motor losses. NEMA motor insulation classes. NEMA, the National Electrical Manufacturers Association, has established 4 motor insulation classes, A, B, F, and H. The specification has standardized on an ambient temperature of 40 degrees Celsius, or 104 degrees Fahrenheit, for all classes. Each class of insulation has a different maximum motor winding temperature rise, in addition to a hot spot temperature, which is an additional temperature rise for the windings that are surrounded by other windings. The maximum temperature rise and hot spot for each class of insulation is as follows. For Class A insulation, the maximum rise is 60 degrees Celsius with a hot spot of 5 degrees Celsius. For Class B insulation, the maximum rise is 80 degrees Celsius with a hot spot of 10 degrees Celsius. For Class F insulation, the maximum rise is 105 degrees Celsius with a hot spot of 10 degrees Celsius. And for Class H insulation, the maximum rise is 125 degrees Celsius with a hot spot of 15 degrees Celsius. In the past, Class F insulation was typically called for in most industrial applications, but with the ever-increasing use of variable-speed AC drives and the associated heating due to harmonics, Class H insulation is now more commonly specified. Electrical motor power ratings. The function of a motor is to perform work, and so one of a motor's ratings should be its ability or potential to perform work. Work is equal to multiplying the applied force by the distance it has been applied. Power is a measure of the rate at which work is being done and is equal to the amount of work done over a given time. James Watt wanted to rate steam engines that he was producing in a unit of power that his customers could relate to. Since the traditional source of power had been the horse, he felt that by quantifying the work that a horse could perform into a new unit of power, the horsepower, and then rating his steam engines in accordance with this new unit of power, his customers could appreciate the capabilities of his steam engines. He determined in practical tests that the average horse could haul coal at a rate of 22,000 foot-pounds per minute. He then arbitrarily raised this figure by a factor of 1/2 to 33,000 foot-pounds in 1 minute, or 550 foot-pounds per second, and established this as 1 horsepower. Horsepower has remained as a standard unit of power rating for electrical motors in North America, while in Europe the kilowatt has become the standard. 1 horsepower is equal to 746 watts, or 0.746 kilowatts. To convert a motor's kilowatt rating to horsepower, one can simply multiply the kilowatt rating by 1.341. Service factor. For a given insulation, a motor with a 1.15 service factor has a lower temperature rise than a motor with a service factor of 1.0. This allows the motor to operate close to the service factor without exceeding rated temperature limits of the insulation. When the voltage and frequency are maintained at the values specified on the nameplate, the motor may be overloaded up to the horsepower obtained by multiplying the nameplate horsepower by the service factor. At a service factor load greater than 1.0, the motor's efficiency, power factor, and speed will differ from the nameplate, but the locked rotor current and breakdown torque will remain the same. Motor thermal limits curves. The motor thermal limits curves consist of 3 distinct segments which are based on the 3 running conditions of the motor: the locked rotor or stall condition, motor acceleration, and motor running overload. Ideally, curves have been provided for both a hot and cold motor. A hot motor is defined as one that has been running for a period of time at full load, such that the stator and rotor temperatures have settled at their rated temperatures. Conversely, a cold motor is defined as a motor that has been stopped for a period of time, such that the rotor and stator temperatures have settled at ambient temperature. For most motors, the motor thermal limits are formed into one smooth, homogeneous curve. The relay's overload element is the main protection element and is the most critical to motor protection. It is always active and cannot be shut off. Motor data sheets should be supplied with every motor. Part of this data should be a thermal limit or thermal damage curve, which indicates the amount of time a specific amount of current can be supplied to the motor without damaging the motor. The cold thermal limit curve indicates the amount of overload current that the motor can withstand before damage will occur when the motor is cold, at the ambient design temperature, which is normally no greater than 40 degrees Celsius. Likewise, the hot thermal limit curve indicates the amount of overload current that the motor can withstand before damage occurs when the motor is hot, meaning it has been running at rated full load current for an amount of time such that the temperature of the motor has risen to its rated temperature above the ambient temperature of 40 degrees Celsius. The acceleration curves are an indication of the amount of current and associated time for the motor to accelerate from a stop condition to a normal running condition. In this particular example, there are two acceleration curves. The first is the acceleration curve at rated stator voltage, while the second is the acceleration at 80% of rated stator voltage. A soft starter is commonly used to reduce the amount of inrush voltage and current during starting. As can be seen on the curve shown, since the voltage and current are lower, it takes longer for the motor to start. Therefore, starting the motor on a weak system can result in voltage depression, providing the same effect as a soft start. The maximum locked rotor stall time for both a hot and cold motor can be read directly from these curves. The most precise way to protect the motor is through the use of motor thermal modeling. It consists of 5 key elements: the motor thermal limits curve, overload pickup level, hot-cold safe stall ratio, unbalanced biasing, and biasing of the thermal model based on hot-cold motor information and measured stator temperature. This all sounds very complex, but actually you will find it very easy to understand. First of all, it should be pointed out that if the motor has been designed fairly conservatively, that is to say that the portion of the acceleration curve under the motor thermal limits curve is less than a third to a half in terms of trip time, and the motor has been applied conservatively, that is to say that during acceleration or running, the acceleration and thermal limits curve do not cross, then thermal model settings can be set fairly easily. If, on the other hand, the acceleration curves and the thermal overload curves are very close, accuracy in the settings becomes very important in order to ensure reliable motor protection without nuisance tripping. We will use the following model to aid in a better understanding of motor thermal modeling concepts. The motor's thermal capacity, that is to say the amount of heat energy the motor can hold, will be represented by the glass vessel. The lava-like fluid filling the vessel will represent thermal energy or heat energy that has been absorbed by the motor. The sources of thermal energy that will fill the vessel or heating the motor are ambient temperature, motor losses due to current unbalances and I²T, motor heating due to a start. Motor cooling will be represented by the vapor evaporating from the surface of the liquid when the motor is running or stopped, which represents the motor's ability to dissipate heat. The fan is representative of the additional cooling effect of the motor's cooling system, which is commonly a fan mounted on the motor shaft. With this model in mind, let's proceed with our explanation of motor thermal modeling. The thermal capacity that has been used is expressed as a percentage of the total thermal capacity of the motor, and can be thought of as the amount of the vessel's volume that has been filled with heat energy. If this imaginary vessel is full, 100% of the thermal capacity of the motor has been reached, and any further increase will result in damage to the motor's insulation. The motor insulation does not immediately melt. Rather, the rate of insulation degradation has reached a point where motor life will be significantly reduced if it continues to run under this condition. Ambient temperature and I²T heating due to motor losses, starting current, and current unbalances start to fill the vessel with thermal energy when the motor current is above the motor's full load current. Once the motor current drops to or below the motor's full load current rating, the thermal capacity used starts to drop. This can be imagined as the thermal energy slowly evaporating from the vessel. The rate at which the thermal energy is evaporated and the final level that it will drop to is a function of the motor data and load current, which will be covered later in this section. The vessel is also emptied when the motor is stopped at a rate based on the stopped cooling time. Motor cooling times. The thermal capacity used value is reduced in an exponential manner when the motor current is below the overload pickup set point. This reduction simulates motor cooling. Both the stopped and running motor cooling time constants should be entered. A stopped motor will normally cool significantly slower than a running motor. We will examine the cooling rate of a motor and final thermal capacity used under two different current conditions, one at 100% and the other at 80% motor rated current. Running cool time. In the first situation, the motor had been in an overload condition, but is now drawing only 100% rated current, which is below the pickup level, and has a hot-to-cold ratio of 0.8. Using the above formula, we can see that at the end of 5 cooling time constants, the motor will have stabilized at a temperature for which 20% of its thermal capacity is used. Note that the motor came within 5% of its running thermal capacity used after 3 time constants. Stopped cooling time. Note that for the GE Multilin 369 and 469 relays, the values of the running and stopped cooling times which are to be entered into these relays must be 1/5 of the actual stopped and running cool times. Now let's examine what happens to the thermal capacity when the motor is stopped, having a cooling time of 2.5 hours. The stopped cooling time constant entered into the relay would be 1/5 of 2.5 hours, or 30 minutes. When the motor is stopped, its thermal capacity used value will decay according to the same formula. If the thermal capacity used were at 100% before stopping the motor, the thermal capacity used will take 5 time constants, or 2.5 hours, to decay. The values to be entered for the stopped and running motor cooling time constants can be calculated by dividing the stopped and running cooling times by 5. For example, if the manufacturer states that the running cooling time is 1 hour, then 1/5 of an hour, or 12 minutes, would be entered into the relay as the running cooling time constant. Now that we understand what the thermal model is trying to do, let's see how it accomplishes this task with the following hypothetical situation. For a given motor, the thermal damage and acceleration curves are shown in this diagram. From a quick look at the motor curves, we can see that the acceleration curve barely fits under the stall limits portion of the thermal limits curve. The protection relay tripped 10 seconds into the start. The customer notes from the relay data that during the start, the motor drew 600% rated current for 4 seconds, and then the current dropped to 300% for only 6 seconds before the relay tripped. Given that the thermal damage curve was selected correctly, the customer wants to know why the relay tripped the motor even though the current draw did not exceed the thermal damage curve limits. The answer is quite simple and clearly explains motor thermal modeling. The area under the thermal damage curve represents the thermal capacity of the motor, and the area under the acceleration curve represents the thermal capacity used to start the motor. During the first 4 seconds of the start, the motor draws 600% current. This current level is greater than the motor's full load current rating, and therefore the percentage of thermal capacity used will increase. The vessel will fill. From the graph, we can see that if the motor drew 600% for 5 seconds, 100% of the motor's thermal capacity would have been used. The motor draws 600% for 4 seconds, so 4/5, or 80% of the motor's thermal capacity was used during this portion of the motor's acceleration. This can be imagined as 80% of the vessel being filled with thermal energy. To determine how long the motor can run when the motor's current draw drops to 300%, the thermal capacity already used at 600% must be taken into account. From the graph, we can see that motor can draw 300% of its rated current for 30 seconds if no thermal capacity had been used. Since 80% of the motor's thermal capacity had already been used, which represents 24 of the 30 seconds available at 300%, the motor can only draw 300% current for an additional 6 seconds. This can be represented visually by moving the area of 4 seconds at 600% current into the area of 30 seconds by 300% current. Now the answer to the customer's question is quite clear. We can see that when the motor's current draw dropped to 300%, the relay could allow the motor to continue to run for an additional 6 seconds before the motor's thermal capacity used reached 100%, at which time the relay had to trip the motor. This is why the relay issued a trip command 10 seconds after the motor started, even though the motor's current draw never exceeded the thermal damage curve limits. In effect, the relay is calculating the integral of the load current. Now that you understand the concept of motor thermal modeling, we will go into the relay setting. The first step in motor thermal modeling is to obtain accurate motor data from the motor supplier. This data must include the following critical motor information: the motor hot and cold thermal damage curves, the motor rated full load amps, the motor's locked rotor current, the motor's locked rotor stall time when hot and when cold, the motor running and stopped cooling times, the service factor, motor thermal rise, and class of insulation. Note that on many large custom motors, this data may not be supplied as part of the delivery package unless requested by the customer. Further, once the motor has been shipped, it may not be possible to get this data. It is therefore critical that the customer makes it clear to the motor supplier the expectation of complete and accurate motor data being shipped with the motor and its importance as a key component of the delivery. Overload curve selection. The modern digital relay has multiple standard overload curves, which can be chosen to provide accurate protection for the motor. In selecting a curve, the engineer would overlay the standard curves to determine the best fit. The overload curve should be chosen such that it is just below the cold thermal limit and above the hot thermal limit. With the hot-cold curve ratio programmed correctly, the overload curves are automatically adjusted whether the motor is hot or cold. In this motor thermal overload curve, it can be seen that if the running thermal overload curve and the locked rotor overload curve were smoothed into one curve, the motor could not start at 80% line voltage without crossing the curve. A custom curve will allow the user to tailor the relay's thermal damage curve to the motor, such that a successful start can occur without compromising protection, while at the same time utilizing the motor to its full potential during the running condition. The custom overload curve feature allows the users to program their own curves by entering trip times for 30 predetermined current levels. Determining the overload pickup. The protection engineer will typically set the overload pickup to 100% of the motor's capability. For motors with a 1.15 service factor, a maximum pickup of 125% of the full load current can be selected, while the maximum pickup for 1.0 service factor motors is 115% of full load current. Having said this, it is common practice to set the pickup to no more than the rated motor full load current plus no more than 10% of the service factor, unless there is another independent measure of motor temperature, such as stator RTDs. If the motor's winding temperature is also being directly monitored by an RTD biasing function to the thermal model, the overload pickup can be safely increased to the maximum allowable value for that motor. Note that the motor feeder cables are normally sized at 1.25 times the motor's full load current rating, which would limit the motor overload pickup setting to a maximum of 125%. Determining the hot-cold curve ratio. The hot-cold curve ratio can be determined from either the thermal limits curves, if provided, or from the hot and cold safe stall times. If the hot and cold safe stall times are used to determine the hot-cold ratio, simply divide the hot safe stall time by the cold safe stall time. If the thermal limits curves are being used to determine the hot-cold ratio, proceed as follows. From the thermal limits curves, run a line perpendicular to the current axis that intersects the hot and cold curves at the stall point. Draw a line from each point of intersection to the time axis. Record the corresponding times, in this case 10 and 15 seconds respectively. The hot-cold ratio can now be calculated as follows. The hot-cold ratio equals 10 divided by 15, which equals 0.67. If hot and cold times are not provided and only one curve is given, verify with the manufacturer that it is the hot curve which is the worst case. If the supplied curve is the hot curve, then the hot-cold ratio can be set to 1:1. Unbalanced biasing. A balanced three-phase system is one in which the phase vectors are 120 degrees apart and of equal magnitude. If either condition is not met, the system is considered unbalanced. The amount of unbalance is calculated by comparing the positive sequence current to the negative sequence current. A positive sequence set of vectors consists of three equal vectors that are displaced by 120 degrees and have a rotational phase sequence of A, B, C. Negative sequence set of vectors consists of three equal vectors that are displayed by 120 degrees but have a rotational phase sequence of ACB. Negative sequence currents, or unbalanced phase currents, will cause additional rotor heating that will not be accounted for by electromechanical relays and may not be accounted for in some electronic protective relays. When the motor is running, the rotor will rotate in the direction of the positive sequence current at near synchronous speed. Negative sequence current, which has a phase rotation that is opposite to the positive sequence current and hence opposite to the rotor rotation, will generate a rotor voltage that will produce a substantial rotor current. This induced current will have a frequency that is approximately 2 times the line frequency, 100 Hz for a 50 Hz system or 120 Hz for a 60 Hz system. Skin effect in the rotor bars at this frequency will cause a significant increase in rotor resistance, and therefore a significant increase in rotor heating. This extra heating is not accounted for in the thermal limit curves supplied by the motor manufacturer, as these curves assume positive sequence currents only that come from a perfectly balanced supply and motor design. The GE multi-lin relay measures the ratio of negative to positive sequence current. The thermal model is biased to reflect the additional heating that is caused by negative sequence current when the motor is running. This biasing is done by creating an equivalent motor heating current rather than simply using average current, I per unit. This equivalent current is calculated using the equation shown. The K factor. The graph on the left shows recommended motor derating as a function of voltage unbalance as recommended by NEMA, the National Electrical Manufacturers Association. Assuming a typical induction motor with an inrush of 6 times FLA and a negative sequence impedance of 0.167, voltage unbalances of 1, 2, 3, 4, and 5% equals current unbalances of 6, 12, 18, 24, and 30% respectively. Based on this assumption, the graph on the right illustrates the amount of motor derating for different values of K entered for the set point unbalanced bias K factor. Note that the curve created when K equals to 8 is almost identical to the NEMA derating curve. If a K value of 0 is entered, the unbalanced biasing is defeated and the overload curve will time out against the measured per unit motor current. K may be calculated conservatively as K equals 230 divided by ILR squared, where ILR is the per unit locked rotor current. For a typical estimate, K equals to 175 divided by I locked motor per unit current squared. For a conservative estimate, K equals 230 divided by I locked motor per unit current squared. Note for synchronous motors, use a K factor of 8. RTD input to thermal memory. GE multi-lin relays also have an RTD bias input to thermal memory function, which also biases the thermal capacity algorithm depending on the stator temperature. When this function is enabled, a second value of thermal capacity used is calculated from the measured stator temperature. This value is used to correct the thermal model, modifying the value of thermal capacity used due to measured, or calculated equivalent, overload currents. The thermal capacity is determined by looking up the corresponding temperature on the programmed RTD bias curve. For example, if the RTD bias curve were programmed as shown, and the maximum stator temperature was 130 degrees Celsius, the corresponding thermal capacity would be approximately 53%. This thermal capacity would then be used if the thermal capacity used from the overload calculation was less. This feedback provides additional protection when errors have been introduced, such as when the cooling has been lost, or incorrect selection of the overload or the ambient temperature is unusually high, etc. It should be noted that the RTD bias feature alone cannot create a trip. If the RTD bias feature forces the thermal capacity used to 100%, the motor current must be above the overload pickup before an overload trip occurs. Presumably, the motor would trip on stator RTD temperature at that time. This completes the motor thermal modeling. Additional induction motor protective elements. Having a clear understanding of the motor thermal model and how to properly set its components provides us with a good start to the process of protecting an induction motor. There are, however, a few additional protective elements which we will examine. Some of these elements, such as instantaneous overcurrent element, are required to provide adequate protection for an induction motor, while others, such as jam detection, are popular options which may enhance the overall protection scheme. The elements that we will examine are short circuit protection, ground fault protection, differential protection, single phase protection, undercurrent protection, and under and over voltage protection. Short circuit protection. The short circuit element provides protection for excessively high overcurrent faults. Phase-to-phase and phase-to-ground faults are common types of short circuits. The short circuit trip element is coordinated with external upstream fuses such that the element will operate first. When a motor starts, the starting current, which is typically 6 times the full load current rating of the motor, has asymmetrical components. These asymmetrical currents may cause one phase to see as much as 1.7 times the normal RMS starting current. As a result, the pickup of the short circuit element must be set higher than the maximum asymmetrical starting currents seen by the phase CTs to avoid nuisance tripping. The rule of thumb is to set the short circuit protection pickup to a value which is at least 1.7 times the maximum expected symmetrical starting current of the motor. This allows the motor to start without nuisance tripping. It is important to note that the device that the relay is to control under such conditions must have an interrupting capacity equal to or greater than the maximum available fault current. Phases directly to the neutral through the earth bypassing the load. This current is sometimes referred to as zero-sequence current. Damage to a phase conductor's insulation and internal shorts due to moisture within the motor are common causes of ground faults. A strategy that is typically used to limit the level of the ground fault current is to connect an impedance between the supply's neutral and ground. This impedance can be in the form of a resistor or grounding transformer sized to ensure that the maximum ground fault current is limited to no more than 10 amps to reduce the chances of metal damage to the motor. There are several ways by which a ground fault can be detected. The most desirable method is to use the zero-sequence CT approach. This is considered the best method of ground fault detection methods due to its sensitivity and inherent noise immunity. All phase conductors are passed through the window of the same CT referred to as the zero-sequence CT. Under normal circumstances, the 3 phase currents will sum to 0, resulting in an output of 0 from the zero-sequence CT's secondary. If one of the motor's phases were to short to ground, the sum of the phase currents would no longer equal 0, causing a current to flow in the secondary of the zero sequence. This current would be detected by the relay as a ground fault. The residual ground fault connection. If the cables are too large to fit through the zero-sequence CT's window, or the trench is too narrow to fit the zero-sequence CT, the residual ground fault configuration can be used. This configuration is inherently less sensitive than that of the zero-sequence configuration, owing to the fact that the differential CTs are not perfectly matched. During the motor start, the motor's phase currents typically rise to magnitudes in excess of 6 times the motor's full load current. The slight mismatch of the differential CTs, combined with the relatively large phase current magnitudes, produce a false differential current which will be seen by the relay. This current will be misinterpreted by the relay as a ground fault unless the ground fault element's pickup is set high enough to disregard this error. Phase differential current protection. This feature consists of 3 instantaneous overcurrent elements for phase differential protection. The differential trip element function can only be used if both sides of each stator phase are brought out of the motor for external connection, such that the phase current going into and out of each phase can be measured. The differential element subtracts the current coming out of each phase from the current going into each phase and compares the result or difference with the differential pickup level. If this difference is equal to or greater than the pickup level for a period of time greater than a user-specified delay, a trip will occur. Separate pickup levels and delay times are provided for the motor starting and running conditions. In this example, both sides of each of the motor's stator phases are being passed through a single CT. This is called the flux balance configuration and is the most desirable owing to its sensitivity and noise immunity. Current unbalance or single phasing protection. The contribution of current unbalance to the thermal capacity used was covered earlier. Here, the magnitude of the current unbalance is used to detect and trip the motor if a single-phase condition occurs. Single phase refers to the situation when one of the three phases is no longer being supplied to the motor. If enabled, a trip and/or alarm occurs once the unbalance magnitude exceeds the current unbalance trip pickup for a period of time specified by the current unbalance alarm trip delay. Under and over voltage protection. In an under voltage condition, the stator field will be weak. To compensate for the weak stator field, the slip will increase, resulting in increased rotor current and rotor heating. If, on the other hand, the motor is in an over voltage condition, the increased voltage produces a marginal increase in field strength, but a large increase in stator heating. The rotor will slip a bit less, resulting in a slight decreased rotor current. The overall result of an under or over voltage condition is an increase in current and motor heating and a reduction in overall motor performance. The under voltage trip should be set to 90% of nameplate unless otherwise stated on the datasheets. Motors that are connected to the same source may experience a temporary under voltage when one of the motors starts. To override these temporary sags, a time delay set point has been incorporated into the under voltage element. The over voltage element should be set to 110% of the motor's nameplate unless otherwise stated in the datasheets. The under voltage element can be considered as backup protection for the overload element. If the voltage decreases, the current will increase, causing an overload trip. In some cases, if an under voltage condition exists, it may be desirable to trip the motor faster than the overload element. Accelerator timer. The relay's thermal model is designed to protect the motor under both starting and overload conditions. The acceleration timer may enhance the motor protection scheme. For example, a given motor should always complete a start within 2 seconds. If the safe stall time is 8 seconds and a failure occurred such that the motor was held in a stall condition, the motor would normally remain at stall for a total of 8 seconds before the thermal model would generate a trip. The accelerator timer could be configured to generate a trip if the motor remained at stall for more than 3 seconds, thereby reducing the stress on both the motor and driven equipment. When enabled, the acceleration timer trip element functions as follows. A motor start is assumed to be occurring when the relay measures the transition from no motor current to some value of motor current. Typically, motor current will rise quickly to a value in excess of the motor's rated full load current. At this point, the acceleration timer will start to time. If the motor's current does not fall below the overload curve pickup level before the program time has expired, the relay will generate an acceleration trip. If the acceleration time is variable, the acceleration timer must be set to a time value slightly longer than the longest acceleration time. Note that some soft starts limit the motor's starting current to less than the motor's rated full load current. Therefore, if the relay does not see the motor's current rise to a value greater than the motor's rated full load current within 1 second after a start, the acceleration timer will be ignored.